I'm Zinyou Wu, the first author of VLDB paper number 2194, Flat, Fast, Lightweight, and Accurate Method for Cardinality Estimation. So this talk will mainly focusing on three parts. First, I will briefly overview the existing cardinality estimation problem, and then I will introduce our newly proposed probabilistic graphical model, factorized sum product network. Later, I will show how to turn this FSPN into a cardinality estimation method for both single table and multi-table join queries. Okay, so cardinality estimation is a critical component of query optimizer in DBMS. It aims at estimating the resulting number of tuples of a query before its actual execution. And it has attracted numerous attention since the recent decades. Numerous ML-based method has been proposed for cardinality estimation. There mainly exist three categories. So model-free methods such as sampling, supervised method regress the featurized query queue into its cardinality, and unsupervised learning method, which will be the mainly focus of our research. So unsupervised learning method basically turns the cardinality estimation problem into a statistical problem. As we can see here, the cardinality of a queue actually equals to the probability of Q on table T multiplied by the total number of a table. Therefore, the core task of cardinality estimation is to build a model to characterize the distribution of T, this distribution, and support inferring the probability of any query on T. The goal of a good cardinality estimator is to be accurate, lightweight, and fast at the same time. So accurate in terms of prediction, lightweight in terms of model storage, and fast in terms of the inference speed, training speed, and update speed. Okay, so how do we build such distribution models? So suppose we have a model with n, suppose we have a table with n attribute, and we want to model its joint distribution. Brute forcefully modeling this distribution is definitely impractical. It's going to take exponential storage. Therefore, we have to have some factorization tools to simplify the joint distribution. The first one is independent factorization. Basically, it's trying to decompose the joint distribution of multiple attributes into their products. A good example of such cardinality estimation using such factorization is histogram, which assumes all attributes are independent of each other. Histogram is very inaccurate, but it is very lightweight and fast. And recently, DeepDB proposed to use sum product network as a new cardinality estimation method. It has a local independent assumption. Basically, it divides the dataset into each small pieces, and for each small pieces assumes the attributes are independent. This method is very effective when there does not exist highly correlated attributes. However, in presence of highly correlated attributes, which is very common, the independent factorization doesn't work that well. It will lead to either large model or very inaccurate estimation. Another factorization tool is conditional factorization, which uses the Bayesian rule and decompose the joint distribution into a smaller joint distribution and a conditional distribution. Several good examples using this factorization for cardinality estimation are Bayesian network and autoregressive models used by Naru and Eurocard, for example. It is not hard to see that both factorization has their own advantage and disadvantages. So is it possible to use both factorization tools? As we can see that the existing method using only one factorization tool cannot build a model that is simultaneously fast, lightweight, and accurate. The answer is definitely yes. Therefore, we propose our factorized sum product network as a new probabilistic graphical model to build model distributions. The key idea of FSPN is to use conditional factorization tools to first separate the strongly correlated attributes from the rest, the weakly correlated attributes. And for weakly correlated attributes, local independence are likely exist. So we use local independent factorization tools, namely FSPN, namely SPN. And for highly correlated ones, their distribution can be easily modeled together, since we can use some dimension reduction techniques like PCA or piecewise regression to reduce the model storage. Okay, we present the formal definition of FSPN here. Let's assume a dataset with two with two weakly correlated attributes and two highly correlated attributes. The correlation among them are also weak. A FSPN model is a well-defined tree structure probabilistic model with 4 types of internal node and 2 types of leaf node here. So the first is the factorized node. So the factorized node trying to separate the highly correlated attributes from the rest using this conditional factorization tools. And for the weakly correlated attributes, i.e. this joint distribution, the left branch of the factorized node will be used to deal with it. Essentially, it's an SPN substructure. So it contains a sum node which splits the dataset until local independence appear, and a product node which detects whether for the current subset of data, there exists some attribute independence. If there exists, then you try to decompose it using independent factorization tools. And when there is only one attribute left, then the FSPN builds a univariate leaf, i.e. a one-dimensional histogram or other parametric distribution functions to directly model its distribution. And for the right branch of a factorized node, we introduce split node, which is different from sum node. It also tries to split the dataset, but it doesn't aim to find independent attributes. It's trying to break the correlations between the highly correlated attributes and the weakly correlated attributes. Until all the highly correlated attributes are independent with the weakly correlated attributes, we introduce a multivariant leaf to directly build distributions using multidimensional histogram with dimensional reduction techniques on the highly correlated attributes. Okay, so FSPN also we provide very effective training process and very efficient online probability inference process. Due to time limit, we will not go too much detail in it. So we directly see our experimental result. We can see we use 2 real-world single-table dataset, GAS and DMV. And on both dataset, FSPN, i.e. flat on single table, achieves roughly the best accuracy with very small model size and very fast training time. More importantly, the inference time is only slower than histogram and much faster than the existing ML-based method. Being able to predict well on single table is definitely not as important, since cardinality estimator has to estimate the multi-table join queries in order to select the optimal join orders for query optimizer. And apparently, we cannot build a model for each possible join of tables. It's going to take the exponential space. Therefore, inspired by DeepDB, we adopt the divide and conquer method to build an ensemble FSPN and to support joint queries. Let's take a very simple examples. Suppose a database with 3 tables, A, B, and C, and table A and B are correlated. The attributes are correlated with each other and not with C. Therefore, we can build a single FSPN model on a full auto join of A, B, characterizing their distributions, and another one for table C. And again, we need to add a lot of fan-out attributes in order to bridge their connections between these 2 FSPNs. So the main contribution of this paper is to propose this theorem, which is theoretically sound for any join queries. Therefore, using our way of constructing this method, constructing an ensemble of FSPNs, the flat method can estimate any join queries. Due to time limit, I will not go into details of this equation. Please refer to our original paper. Thank you. So for the multi-table experiment, we use the well-known IMDb dataset and job light, job hours, 2 well-known query workload. We can see that flat also achieves the best accuracy on both workload with relatively small model size and fast training time. Again, the inference latency is still the fastest, and also it has a very efficient updating method, results. Okay, at last, we integrate flat into Postgres, and we can see that it improves the Postgres baseline by 13.4%, which is slightly better or comparable to the previous SOTA neural card. And more importantly, it is very close to the true cardinality, which represents the best the Postgres method can ever achieve. Therefore, we can see that the flat can be a practical counterpart of Postgres cardinality estimation. Thank you.